we start permutations first. So you can see the permutation, this concept plays an extremely important role here. All right, first, let us count number of permutations. That's easy, very basic knowledge you should have from discrete math. Okay, yeah. So given permutation like this, okay, so n symbols, n symbol permutation. Yeah. The question, how many number of permutations for n elements? I think you all know the answer. Yeah. The answer is n factorial. So here I think I do not need to derive it. Okay. Yeah. Because so easy. Yeah. But what is the conclusion for this answer? That's more important for us. We need to have some conclusion that can help us to solve this lower bound problem. That is very important. Yeah. The conclusion is there are n factorial possible outputs. N factorial possible outputs. You cannot have more than n factorial outputs, right? You cannot have more than n factorial outputs. So that's important. Okay? So that means the number of leaves in the decision tree, should be at least n factorial. You need to cover, because each leaf corresponds to one output. Yeah. So let me go to print. Yeah. Each leaf corresponds to one output. So all the leaves in your decision tree should cover all these possibilities. So that's why you should have at least this many leaves. So that is the main conclusion we want to have. Yeah. Next, let us study binary trees. Yeah. All right, so let's look at relationships. Yeah. Some properties. Each output corresponds to one leaf. Yeah. First observation. Second, the height of the decision tree corresponds to the worst case performance or efficiency. Okay? Yeah. So that's the simple observations. Yeah. Now for a typical decision tree. So this is a general decision tree like this structure. Let us look at the number of nodes in each level. The largest possible number of nodes at each level. Okay. Level 0, the root, only one node. Okay, 2 to the 0 power. Level 1, 2 to the first. So 2 nodes. Level 2, at the most, 2 square, and so on. Okay. Level H, the height. So starting from 0, the bottom level height H, level H, 2 to the H power. Okay. So at the most, so that means the maximum number of nodes in each level. Right? All right. Next, let us look at the number of leaves in the decision tree. Okay. Can we estimate that number? Right? So our estimate is the number of leaves, little l, less than or equal to the number of nodes at the level H. Why is that? Why is that? Can you see this inequality? This is a key inequality. So we have to understand this inequality before we can get our powerful result. Yeah. So let me explain this result first. First, let us assume a special case. All the leaves are at a level H. That's a special case, not a general case. In that situation, how many leaves do we have? This number. Okay. All right. Then, now we consider the general case. So not necessarily all the leaves at height H, level H, could be in higher levels, but when you go from the lowest level, level H, to higher level, you will reduce the number of leaves, because 2 leaf nodes will merge to 1 possible. You only merge number of nodes. When you merge 2, you reduce the total number of leaf nodes. So if you look at it in that way, so for the general case, what you have is L less than or equal to 2 to the H. Because when you go higher level, you need to merge nodes, right? Yeah. Look at here, So if we imagine, so there are lower level like that, okay? How do we get this one? Because we merge these 2 to get this one. We merge these 2 to get this one. Merged to get that one. So we will reduce the number of leaves, right? So based on this observation, so you can see that total number of leaves can only be smaller than the maximum possible number of leaves you can have in a decision tree with height H. Okay. So we get this critical inequality for our result. Then we take log base 2, both sides, we have this inequality. But H, we know H must be an integer, so we can take the ceiling function. Yeah. But I want to mention here this result, these two are true for all binary trees. So not necessary full binary trees. So all binary trees, we have this result. Okay, yeah. So we can prove easily. Yeah. So we will later, when we have the situation for all binary trees, we can apply this inequality here. Okay. All right. Next, we can derive the lower bound for the worst case of comparison sorts. How do we do that? We estimate the height of a decision tree. Okay. All right. So after we do the analysis, now we can connect the pieces. Yeah. Given a comparison sort, so let us draw a decision tree, general decision tree for it. Yeah. All right. Now we know the leaves contain all the permutations, right? So we did this observation before. The leaves of that decision tree should cover all the possible outputs. So that's why we can say the leaves contain all the permutations. Yeah, that must be true. Yeah. Then if we count the number of permutations less than or equal to the number of leaves. Less than or equal to. Okay? Why less than or equal to? Why it's not exactly equal? Yeah, the argument is like this. Argument. Not exactly equal, less than. It could be less, strictly less. Why is that? That based on another observation. Because some permutations may be repeated for a bad algorithm. Because here we talk about a general comparison sort. That comparison may not be optimal. The general comparison could be a bad one, not efficient. There are some redundant comparisons. People may do some redundant comparisons. So in that situation, So some of the permutations could be repeated more than once. When that happens, the number of leaves strictly less than number of permutations for that kind of redundancy. Yeah. All right, but we have this less than or equal, so that must be true. Okay. Then, based on the result from the previous slide, we can get the conclusion. Number of permutation that equals n factorial. Less than or equal to L, but the L less than or equal to 2 to the h, the height h. Okay? So then, if we take log base 2, we get h greater or equal to the ceiling function of log base 2 of n factorial. Okay? So here you can see we estimate the lower bound of h. This is the lower bound. Okay? And this lower bound, which asymptotic class does it belong to? You know, based on our knowledge, we learned it before, n factorial, log n factorial. So we did before, right? Stirling formula, we also know we can use that. That is in right, big omega, right? So, you know, big omega, we know it's lower bound is this. Lower bound is this, right? So the lower bound, big omega, is n log n. But this height is for the worst case, right? Height is for the worst case. So the worst case has this lower bound, n log n lower bound. Okay? So what is the conclusion can we get from this result? This result is very nice. This is a super nice, great result. Why this result is so good? First, for any comparison sort, okay? Any comparison sort, you cannot get a lower bound better than n log n. In other words, the worst case performance cannot be better than n log n. So that is the first comparison, the worst case. Yeah. Second, this lower bound we can apply to, you know, some examples. All right. First, let me try several simple examples. When n equals 3, what is 3 factorial? 6, right? What is the ceiling function of log base 2? 6. 3, right? Yeah. So that means the worst case, the best worst case you can get for any comparison sort for 3-element array is 3. You cannot do better than 3. Okay? Let us consider n equals to 4. What is 4 factorial? 24, right? What is the ceiling function of log base 2? 24. 5, right? Yeah, because 32, power ceiling function, 5. That tells us to sort a 4-element array, the best you can do for the worst case is 5 comparisons. You cannot use 4 comparisons to solve arbitrary 4-element array. That's simple. Okay? All right. Another one. When n equals 5, what is the 5 factorial? 120, right? What is the ceiling function of log base 2 of 120? 7, right? Because 2 to the 7, that's 178. Okay? Yeah. This tells us to sort a 5-element array, the minimum number of comparisons you need 7 for the worst case. You cannot use 6 comparisons to sort arbitrary 5-element array. You cannot. Using the comparison sort, okay? Remember, this result is only true for comparison sort. Yeah. And so on. So here, that should be enough. So these examples, so let you know how powerful, how important the result we get here. Okay? All right. So this is an important result. So I emphasize a lot. Yeah. So you should understand very well. Yeah. So we complete this topic. Then we have the last part of today, B.5. We will study the search algorithm. After the sorts, we want to study the search algorithms using the decision trees. Yeah. All right.